In this video, I'm going to talk about bosons and fermions in terms of identical particles. So if you have watched my previous video, you will know that we have two particles and the number one. So number one particles, it's phi A R. The second particle is phi B R, right? Phi A and phi B here represents two different states. And if you recall from my previous video, I talk about how phi R1, R2 can be written as a product of phi A R1 and phi B R2. I talk about this in my previous video. If you guys don't know where this is coming from, I recommend you guys go to watch it. But anyway, we should continue with this, right? We're not talking about the time part here. We left that out for later, but assuming that we start with this formula. So what this formula tells us is that one big assumption from this formula is that we can tell the particles apart, right? Because if we aren't able to tell the particles apart, it wouldn't make any sense to claim that particle 1 is in state psi A or particle 2 is in state psi B. Then all we ever could say is that one of them is in psi A state, the other one is in psi B state, right? So one thing very fundamental about quantum mechanics is that particles are indistinguishable. So you cannot really say here's electron A and here's electron B. But you can't really do that in quantum mechanics because every electron are the same. So they're indistinguishable. So that is not the case in classical mechanics, because obviously in classical mechanics, if you have two balls, right, you paint one of them red, you paint the other one blue. You can name the red one ball 1, you can name the blue one ball 2. So they are in fact distinguishable. But in the case of quantum mechanics, particles, this including protons, photons, electrons, whatever particles that you can think of, they're all indistinguishable. Means that you cannot tell them apart like you do in classical mechanics. So the fact that we cannot tell them apart, or that the particles are indistinguishable in principle. So when we construct a wave function, we need to construct a wave function that is non-committal as to which particle is in which state. So the formula given for this is the following. So phi plus minus R1, R2 is equal to A, some constant A, phi A, R1, phi B, R2, plus minus, I'm going to explain the plus minus part in a bit, but plus minus phi B, R1, phi A, R2. So what is the point of this formula? What the point of this formula is that it includes both possibility. So if we cannot tell the particles apart, we must have a formula that represents a superposition of the both possibility, right? So there are two possibilities here. The first possibility is that particle 1 is in state A and particle 2 is in B. So this is the first possibility. The second possibility is that particle 1 is in state B and particle 2 is in state A. Right, so these are the two possibilities that we have here. And since that we know in principle that particles are indistinguishable, so we must have this formula here that allows both possibility, in which I have listed them here, right? Because in the classical sense, if you were talking about classical mechanics, you could tell the balls or particles apart, then you wouldn't need a formula that includes both possibility. But since here we cannot tell the particles apart, we need to have a formula that includes both possibility of the two particles existing in different state, as I have written down here. You guys can pause the video and try to digest what I said, and then we can move on. So let's move on. So back to the original starting topic of the video, which is boson fermions. So according to quantum mechanics, there are only two kinds of identical particles, bosons and fermions. So any particles you ever heard of, so there's proton, there's photon, there's electron, there's even maybe you heard of graviton or gluons, right? All of these particles can be classified to be either a boson or a fermion. So for a boson, so bosons are particles with integer spin. So the spin of boson is always an integer. So the spin is like 0, 1, 2, blah, blah, blah. So if the spin is the following for that particle, then it is what we call a boson. And fermions are particles with half integer spin. So the spin for fermions are like 1/2, 2/3, and blah blah. It keeps going on the list. So basically, every particle we know can be classified to be either a boson or a fermion. And what does that have anything to do with the formula that we have here? Well, something very important is, let me write this down, is that bosons are symmetrical under interchange. So what do I mean by that? Well, remember our wave function here, we're talking about two identical particles, right? So if these two identical particles are bosons, then this plus minus sign in our equation, so here's one, here's the other one, they become positive. So if there were to be a fermion, it becomes negative. So let's look at the boson's case. So for boson is plus. So this is our formula for bosons. Plus phi b r1 phi a r2. So bosons are symmetrical under interchange. What that means is that if you swap spatial coordinate 1 and spatial coordinate, so if you swap r1 and r2, they result in the same thing. So let's look at the case if we swap r1 with r2. So r2 becomes the front, r1 at the back as the second one. So what is this going to be? Well, this is now going to be phi a r2 psi b r1 plus phi b r2 phi a r1. So these two are exactly the same, right? Because as you can see, so in this case, in this one above, what we have here is psi a r2 plus phi b, psi a r1 plus phi b r2, and then look at what we have here in the second equation, right? Is phi a r1 phi b r2. So these two are the same, and then the same goes for these two terms. So these two are the same. It's getting kind of messy here. I'm doing too much stuff, but the key takeaway is that when the two identical particles are bosons and you swap them, you swap these two particles, nothing changes to the wave function. They remain the same. So these two are exactly the same before and after you swap them, because they're equal to each other, and these two terms are equal to each other. So therefore, for bosons, nothing happens when you swap the particles. So they're equal to each other. But very interestingly, that is not the case for fermions. So let's look at what happens with fermions. So for fermions, if we use the same formula, now we use negative. Let's look at the case of R1, R2. Well, this is going to be equal to, or some constant again, phi A R1, phi B R2, But in this case, it's going to be minus, because remember I talked about bosons are positive, fermions are minus in this case. And then we have a minus sign in the middle, so minus phi b r1 phi a r2. And let's look at the case for r2 r1 instead of r1 r2. So r2 r1 is going to be equal to a phi a r2 phi b r1 minus phi b r2 phi a r1. And if you pause the video right here, you can see that these two are actually not equal to each other, unlike the cases for the boson. These two are not equal to each other. So what happens here is that our second scenario of psi r2 r1 is actually equal to the negative of the first case scenario, because if you look at what we have here, let's move this down. Let's do that. So let's copy it and then paste. Right? If you multiply this expression here by a negative, then you get, well, negative phi a r1. No, phi 2, phi a r1, phi b r2. And you get plus phi b r1 phi a r2, right? So now this is equal to what we have here, right? Because as you can see, so phi a r2 phi b r1 and phi a r2 phi b r1. So these two terms equal to each other, and we have negative psi b r2, and in this case negative psi b r2 phi a r1 phi a r1. So unlike bosons, when you swap the particles, when you swap two identical fermions, it actually changes the sign of the wave function. So in this case, phi minus r2 r1 is equal to negative phi r1 r2. So this is unlike boson, because remember what we have for boson was that when you swap these two r1 and r2, the spatial coordinate for particle 1 and 2, like, it doesn't change anything. But for the case of fermion, it does. When you swap these two, you need to change the sign, and they're opposite of each other. And if we move on to the next topics, it's very interesting because you guys might have heard this multiple times. There's a principle by a very famous physicist, Pauli, that is called the Pauli exclusion principle. You guys might have heard of this, but it says that like no two electrons can occupy the same state, but that is in fact not correct. Well, it is correct, but it is not the whole. A more precise definition would be that two identical fermions cannot occupy the same state rather than two electrons. But electrons are fermions, so that is correct too. But it's just not as precise as two identical fermions. So Pauli exclusion principle tells us that no two identical fermions can occupy the same state. So why is that? You can actually tell from the formula that we have here. So our formula goes, so we're talking about fermion here, so it's the negative, right? If psi A is equal to psi B, what this implies is that same state. And then if we have the case for a fermion, we start with this what we write down for fermion. I think I can just paste here of what I written up before, right? So this is what we have for the negative, right? So this is equal to psi negative r1 r2. So let me ask you, what happens when psi A is equal to psi B? Well, if psi A is equal to psi B, then this becomes psi A r1 phi A R2 minus phi A R1 phi A R2, right? Because since if psi A is equal to psi B, then you can interchangeably swap any psi A or psi B to any psi A or psi B, right? You swap any psi A to psi B, or swap any psi B to psi A, or to itself too. So then what is this equal to then? Oh, one thing I forgot was that there was meant to be a function, a constant in front of it, A. But that's not the main point here. But what you get from inside is actually 0. So that's outrageous, right? So when you have two identical fermions occupying the same state, our assumption, phi A is equal to phi B, we're left with no wave function at all when you plug it into this formula. So that's very problematic. And that is the famous Pauli exclusion principle, which states that no two identical fermions can occupy the same state. So electron cannot be in the same, so for example, two electrons cannot occupy the same state. So that is the famous principle. And now we can move on to look at an example. This example I'm going to talk about is from the textbook. So suppose we have two non-interacting particles, both of mass m in the infinite square well. You guys might have remembered this from was it chapter 2 or chapter 3 that we talk about and particles in infinite square well. Then we want to know the one particle states. Then the one particle state is what? Is. So recall that the solution to a particle in an infinite square well, so this should be something that you should be able to remember. So phi n, so I'm writing down the solution to a particle in an infinite square well. A square root of 2 over a sine m pi over ax, where the energy En is equal to n squared k. So if the particles are distinguishable with number 1 in state n1 and the number 2 in state n2, then our wave function is a simple product of the two, right? I talked about this at the very beginning. So for this case, it would be psi n1, n2, x1, x2 is equal to the product, so psi n1. So what we have done here is broken the wave function from one that composed of two into two individuals. And the energy would be n1, n2 would be n1 squared plus n2 squared k multiplied by k. So we've broken it into the product of these two. So if the ground state, so phi 1, 1, what would that be? Well, that would be 2 over a sine, because we're talking because there's no more negative, I mean the square root here, because we're talking about a product of two, right? So sine 1, 1 would be sine 2 over a, because this is the result of square root of 2 over a times square root of 2 over a, sine m pi x1 a times sine pi x2 a. Now there's no n here because n is just 1, right? So this is what we have here, and then and the energy here is going to be just 1 squared plus 1 squared. k is equal to 2k. And for 1, 2, this is going to be 2 over a sine pi x1 a sine 2 pi x2 over a, right? Because n is equal to 2 in this case. And our energy is going to be 1 squared plus 2 squared is equal to 1 plus 4, or times k is equal to 5k. And the same goes for the state di 2, 1. This is going to be equal to sine 2 pi x1 a sine pi x2 over a. And the energy is going to be same as 1, 2, which is just going to be 5. So now let me ask you, if the two particles are identical bosons, what happens? Well, remember, if they're bosons, right, then if we look at the formula that we have all the way up here, this formula right here, well, our a in this case would be square root of 2 over a. Well, in this case, if you use that formula for bosons, it's going to be square root of 2 over a sine pi x1 over a sine 2 pi x2 over a, right? Because remember, when it's a boson, then you swap the particles themselves, nothing happens. They're before swapping is equal to after swapping, with energy is equal to either 2k or 5k. But now is the very interesting case, which is that if the particles are identical fermions, so according to the formula all the way that we have all the way above, this is going to be equal to sine pi x1 a sine 2 pi x2 over a minus sine 2 pi x1 a sine pi x2 over a. But very interesting is that, remember from the Pauli exclusion principle, that no two fermions can occupy the same state. So that impacts our energy, because remember, we have to look at 3 different scenarios, and one of them being when 1, 1. When you have both in state 1, when you have both particles in state 1, then the total energy is going to be 2k. But because of Pauli exclusion principles, for fermions, two identical particles can never be in the same state. So for fermions, you will never have 2k for fermions. It's always 5k for either 1, 2, or 2. But that is not the case for boson, because for bosons, 2 bosons can occupy the same state. So 2k does exist for boson, but not for fermion. And that is a pretty important implication of the Pauli exclusion principle. And I'm gonna end my videos here. And if you guys have any question about anything that I've talked about in this video, feel free to comment down. And I'll see you guys next time.